In this video, we're going to state a very simple theorem, and we'll prove it using the well-ordering principle. It's fairly intuitive if you think about this. It says if k is a natural number, 1, 2, 3, dot, 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 then there exists some integer that's greater than or equal to 0, and t, an odd natural number, such that this number k is equal to 2 to the nth power times that odd positive integer. So let's just think of a couple. Let's think of a simple case. Let's think of k being a prime number like 7. Well, can it be written like this? Well, sure. I mean, k is odd itself, and m is allowed to be 0, so 2 to the 0 times 7 is equal to 7. So we've proven that that works for a prime number. Let's pick a number like 20. K equals 20. Well, what does that imply? Let's see, it would be 4 times 5. That would be 2 squared times 5. 5 being equated to t here, the odd positive integer. In this case, it was 7. So the two examples I've written make it look like it's feasible, and I guarantee it's true, but we are going to now prove it. So what am I going to do? I'm going to end up using a proof by contradiction. I'm going to define this set S to be all of the numbers, the natural numbers k, for which this fails. So here's the definition. You need to look at this for a little bit. Capital S is the set of all the natural numbers such that k, each natural number in this set, k, is not equal to 2 to the m times t for any m greater than or equal to 0 and any odd t. Okay, so we're taking S to be that complete set. So S is obviously a subset of the natural numbers. And so, to the contrary, what am I going to suppose? To the contrary, I'm going to suppose that there are actually numbers in S. I'm going to suppose that S is not the empty set. I know it is because that's what we're trying to prove. But to the contrary, let's just suppose that it's not, and we'll reach a contradiction. So if it's not, that means there's at least one element in it. Let's say, since it's not empty, we're going to say by the well-ordering principle, remember what that is? That means since S is a subset of the natural numbers, it has a least element. By the well-ordering property, set S has I'll call it a least element, a smallest element. And let's just give it a name. Let's call it script lowercase l. Now, I got to think good on this one. Since L is equal to 2 to the 0 times L. Hopefully that's obvious. 2 to the 0 is just the number 1, so that would hold for any real number actually. L is equal to 2 to the 0 times L. And it is in this set. What does that tell us? L is the smallest element in this set. So L is not equal to 2 to any non-negative integer, including 0, times any odd number. So what can we conclude from this? Here's 2 to a non-negative integer times, and this L corresponds to t. So that means that t, in this example, that L has to be an even number. Since L is equal to that, and I'll even say, and L is an element of S, just to emphasize this, L must be even. And that's all because how we define this set capital S. Just to reiterate one more time, L is in this set, so L can never equal 2 to the m times t, where m is 0 or greater and t is an odd number. Well, here's 2 to the m, it's greater than or equal to 0, and L, so L cannot be an odd number. L must be even. By definition of even, let's let L equal 2R. For some R in the natural numbers. Okay, so it's even. So it's equal to 2R for some, and I'm just going to make a note. R is less than L. Because L is a positive number, and it's equal to 2 times R. So R is obviously less than L. So what does that tell us about the number R? Well, it's definitely not in this set, because L is the smallest number in this set. And if it's not in this set, that means that the condition holds. So this would so R would satisfy this if I replaced K with an R. Okay. Thus, R is not an element of S. I'll just end it at that because of that reasoning right there. There's no positive integer smaller than L that's in this set, because L is the smallest. Okay, since it's not in there, R satisfies this statement up here. All right. Thus, I hate to use 2 sentences in a row with thus, but I'm going to. R is not in S, thus there is an m, I'm going to call it m sub 0, corresponding to this one, a non-negative integer, and a t0 in the naturals, where t is odd, such that that equation holds, such that R is equal to 2 to the m naught times the odd integer t naught. Since R is not in this set S, there is an R equal 2 to some m greater than or equal to 0 times an odd integer, odd positive integer. Well, that almost completes it. Therefore, one more sentence. L, which we know is equal to 2 to the R, and we know R is equal to that, which would be 2 times, I'm just going to substitute that in for R, 2 to the m naught t. And what is that equal to if you multiply this through? 2 times 2 to the m naught, we get 2 to the m naught plus 1, some other positive integer, times t naught. So this implies that L equaling 2 to this positive integer times an odd positive integer, that means that's exactly what it means to be in this set. Let me restate that. That's means that L cannot be in this set because L, this inequality did not hold for any M or T at all. L was never equal to 2 to the mt, where m is greater than or equal to 0 and t is odd, and we just concluded that it is. That is a contradiction, for which we can conclude that our to the contrary statement is false. So therefore, that contradiction means that S is the empty set.